right. With that, I think maybe we can switch gears. So we have another guest speaker. We have Dennis on the line. I guess I don't know if it's the line, the phone. It's not a phone. All right. Anyway, on the computer screens. But he is a graduate student, also at Stanford, obviously, and so he will give us sort of a talk on how he does characterizations and how he is trying to improve computing power. All right. So,
hey all.
So this is Dennis, and yeah, you should have hosting ability and things like that. So
great.
Okay.
Thank you, Angela, for putting this together, and thank all of you guys for coming out. I think it's really cool what we're doing here. So I'm going to be talking and sharing my screen a little bit. Angela, it says I can't share my screen at the moment.
Okay, hold on. Sorry.
No problem.
I made you co-host. Just kidding.
There we go.
Now we're there.
All is well. Right. So I'm going to go a little bit into my research, and we're going to be touching on a bunch of different topics. So I think I can set it up. Maybe I'm not sure if I can see the chat like we are. So if you guys could just unmute yourself if you have any questions during the talk.
Yeah, and I can monitor it for you too.
Oh, that would be great. Yeah. So if anyone has any questions, don't hesitate to stop me. We're going to be jumping, through a decent amount of different topics, and I'm happy to stop and discuss whatever you guys want to. So with that out of the way, the first, there's a picture of me. But what I'm going to be talking about is basically a new way of doing computer memory, how we can make computers faster. But there's a lot of background we need to get to before I get to that. So we'll start off at the very beginning. I am basically in the subfield of nanotechnology that works on making computers go as fast as possible and use as little energy as possible and work really well. And specifically, you can think of a computer as basically having two parts. They have the transistors and the memory, and they're basically analogous to the functions of your brain. Your transistors are the part of the computer that does what your brain does when you're, say, thinking really hard, trying to figure out a math problem or something. And your memory is, of course, your memory when you're recalling, say, what you did, what you had for lunch. So I am specifically focusing today on memory. Transistors, a lot of people also work on those. That's, of course, a very big field. But memory is also super interesting and a big part of computing. And so we want to make memory work really efficiently and quickly. So first off, before I talk about the many different ways to make memories work in computers, I'll first tell you what it is. And give a couple examples of what it has to do. So very simply, memory can be a couple different things. In terms of modern computers, all modern computers work in binary, ones and zeros, base 2. And that's because it's much easier to work with things when they're not, all noisy. Either something is a 1 or it's a 0, and so that's much easier to deal with for computer designers. So for a binary memory that needs to store either a 1 or a 0, it just has to have two operations. First, it has to have a write operation, and then you can see that on the left where you have your memory cell, that blue box. You have to be able to put either a 1 or a 0 into it, and in this graphic, it's a 1. And for the read operation, of course, you have to be able to look into that cell and see whether it's a 1 or a 0. And memory, especially today, is getting a lot of attention because machine learning in particular is extremely memory intensive. I expect most of you guys have heard of machine learning, especially out here in the Bay Area. It has, huge market potential, and it's already widely in use across, many of the biggest companies in the world today. But this isn't a talk about machine learning. But the pertinent feature of machine learning is that it uses a ton of memory. The more memory it uses, the better. And so the better we can do memory, the more machine learning we can do. Now, of course, there are many other applications of memory, but that's probably the big one today. So here's one example of modern memory system, and this is widely in use today. A solid state drive. You have them in your laptop, most likely, and there's they're in flash drives. They're everywhere, and the concept is actually very simple. In a given memory cell of a solid state drive, you either have an electron, that's a 1, or you don't have an electron, that's a 0. So it's like you have a little box, and you put the electron in the box simply by applying a voltage that's there on the left. But the interesting thing is how you check whether an electron is in the box. That's the read operation. So you can basically apply a slightly smaller voltage, and the electromagnetic waves that pass across the box are changed based on whether or not there's electron in it. So you have a detector for the waves there, and if the waves are large, that's a 1, and if they're small, that's a 0. So I think this is, basically a very simplified picture of how solid state drives work, but it does get the point across of, what we're talking about when we talk about memory. And there are a million ways to do memory. Way back in, far in the past, maybe the early 1900s or so, we had record players, and that was an example not of a binary but of an analog memory. But more recently, you have floppy disks, which work as, if it's polarized this way, it's a 1. If it's polarized the other way, it's a 0. You have something called DRAM, which is if there's electrons on a capacitor. So there are really a ton of different ways to do memory, and even in computers today, there are a bunch of different styles of memory that are all used in a single computer. So this is just an example of maybe one of the biggest ones, but there are a ton. And so now we finally get to another type of memory, which could be phase change memory. And that's not, is there an electron or not? It's not, is it magnetized this way or that way? It's, is it in this phase or that phase? And so you guys all know the solid and liquid phases. And you could of course assign a 0 to be the state if your water is ice, and 1 if your water is liquid. But you can't have liquid water in computers. So what we actually use is a material, germanium antimony tellurium, or GST, and the S is because antimony is abbreviated SB for reasons unknown to me. But so GST is a material that functions this way, except instead of solid and liquid states, it goes from amorphous on the left to crystalline on the right, and both are solids. So maybe using the word phase isn't the best, but they are changing their organization, and we can tell using nano characterization exactly what state they're in. And so this functions well as a memory. But first, I want to talk, maybe when I say the word characterization, you probably think, they probe it with, with their fancy gadgets, and they see what's going on. But I want to emphasize another aspect of characterization, which is simulation. There is never, no good research project will ever do characterization without some simulation to back it up and make sure that they're understanding what's going on is correct. So the basic idea of simulation is you take in a system, you put in mathematical equations that describe the system, and then you let a computer kind of iterate on those equations to see what the final state is going to be. So here in this box, you're typically going to see, just with very simple equations, what particles are going to do in that box. And that can give you both predictions, which is maybe what you think of, but it can also give you verification of results, which is also hugely important. You know, no one's going to trust a simulation on its own that gives some cool result, but also it's hard to trust characterization on its own without some simulation to back it up. Everyone needs to explain in terms of both simulation and characterization the results they have for it to be trusted. And so I'd also like to point out that these pictures I showed you last slide were done using simulation. So of course the equations were a bit more complicated, you know, a bit of quantum mechanics and chemistry in there, but we are able to simulate exactly what the molecules in GST are going to do under these circumstances. And so with that simulation, I'll finally get to why phase change memory is so cool. I've kind of just been saying it's, you know, it exists as another way to do memory, but here's why I think it might be better than other ways. And that is because phase change memory can actually be in multiple different states. Not just 0 or 1, but maybe 0, 0.5, and 1. And you can treat all of those as separate states. So the example I'll use to explain why this is better is when you store a phone number in base 10, you know, your phone number, that's 10 digits, right? And so it would require that amount of physical space if you had a storage method that stored a digit in each cell. But with binary, that's base 2, so it stores either a 0 or 1 in each cell. And so there your phone number has to be about, I think, 34 memory cells. But if you could store 3, it would go all the way down to about 22 memory cells to store a phone number. So you require less memory cells to store the same amount. And there's a bit of overhead, but really you're just getting more for less. And so it becomes cheaper, it becomes faster. And as I mentioned for machine learning, we need a lot of space. And with this, we might be able to get there a lot more quickly. So that middle state, what I'm talking about is kind of in between amorphous and crystalline state. So it doesn't just quickly go from solid to liquid like water does. There's an in-between area, and we can take advantage of that. So finally, I'll go a little bit into how you characterize it physically to go along with the simulation. And this is not strictly what we use. This is kind of I'm going to show a picture on the next slide, and I want you to understand how it was taken because it wasn't just taken using a camera. But scanning electron microscopy, or SEM, is used. So instead of when we see something, photons come from, you know, our electric light or from the sun. They bounce off something and then they hit our eye. SEM is the exact same thing, except instead of photons, instead of light, it's just electrons coming through an electron gun, bouncing off the object and hitting a detector, which converts into light. So it's a pretty simple process to understand. I would call it, you know, one of the most basic units of nanocharacterization. If you need to see something and you don't want to work too hard at seeing it, SEM is typically the way to go. But this is an example of a picture taken using SEM. You can see the units of scale there, and I don't know if you probably have gone over micrometers and nanometers and exactly how small they are, but this is a very small picture. And there is a tiny bit of phase change material in this picture, and that's because this is an example of a characterization structure we would use on phase change material. Basically, in the top and left, you have one pair of probes, and in the bottom and right, you have another pair of probes, and that's so we can independently control the voltage and the current, the electrical characteristics going through that phase change material. And by varying exactly how much current I put through the phase change material, I can vary exactly where it is on that sliding scale of crystalline to amorphous. So I can get to that 0.5 state by applying slightly less current, and I can get to the 1 state by applying more current. And then using the voltage probes, I can measure how I've got there. So the cell, the phase change material, changes its electrical properties based on what crystalline state it's in, and I can measure that all using this 4-point structure. So all that being said, this is where I am today. I use that structure I showed on the previous slide, repeated, many different times. So I have many different memory cells, and I perform, repeated electrical tests on those memory cells to see if I can reliably achieve multiple bits per cell. And there you can kind of see some of the equipment I work with. On this test board is the chip itself, and inside the chip itself are all these phase change memory. And this system right here is how I interface with that and how I, apply electrical signals to the chip itself. And that's me on the left. And so I'm going to end it off here with an example of some real data that I actually got. And I believe you can understand it, pretty much fully in terms of what I've talked about today. On the y-axis, you see the level of crystallization. So if it's fully amorphous, it's all the way down here, say a 1. And then by varying that current using that 4-point structure that I described, you can move it up in resistance, which is equivalent to crystallization, to that 0.5 state, and finally all the way up to the 0 state. And this was all done on many different cells using that 4-point structure. So that's all I have. And I would be happy to stay and take questions and talk about whatever you guys want. Thank you.
Great. Thank you, Dennis. Thank you for taking the time to explain what's happening. So does anyone have any questions on this? I know it's a pretty abstract and really, I think it's a really interesting topic because it's talking about something that's deep inside of the computer that I think I personally never think about. So if anyone has any questions or comments or wants any sort of clarity on anything, Dennis is here to answer all of those questions for you. Even, how does this part work?
Okay.
So
yeah.
I actually, go on.
Okay, I have a question for Dennis. Thank you, Dennis, first. You explained that very well. I used to work for Maxtor, company that used to need hard drives and how to store data. And this question is just out of curiosity. I know you are in the electronic field. Since we are talking about the nanoscience, like when we look at storing memory in our brain, for example, I'm looking at you, my eyes are converting your image into electrical signal and telling me I'm looking at Dennis Rich. But also, if I see you after a month, that memory of you probably say, oh yeah, I met him over the Zoom, I saw him. So now comparing this storage system that you just explained, will there be a day that we can extract information from the brain? Like, when we put a flash drive in a computer and remove that information from hard drive to a flash drive. So do you foresee that or might happen one day that we can read people's mind? Or whatever, the memory?
I have a couple different ways to answer that question. The first and the most real way to answer that question is I have no idea. That's not really what I do, but maybe a more interesting way to go. There is a subfield of memory and computing called neuromorphic computing. And so that kind of attempts to mimic a little bit the structure of the brain. So one thing about the brain is that everything I told you about today was digital. Record players in the past were analog, but the brain is also analog, right? So all of our most advanced computers are binary and they store things as 1s and 0s, but the brain is analog. So some people think that in order to get the most efficient computing possible, we might actually have to return to analog computing and find new ways to make it work and get over all the problems that caused us to switch to binary in the first place. Because it does offer significant advantages. So with neuromorphic computing, we might be able to do machine learning a lot faster than in the past. But to answer your direct question, about whether we'll ever be able to interface with the brain directly. I know, the capacity of science is boundless, but I don't know if it'll happen within our lifetime. I would love to see it happen, but I don't know.
Hope it happens in my lifetime.
Yes, that would be cool.
There are things like I've seen or heard of studies where they will inject or basically put a fiber optic cable into a mouse's brain and can stimulate certain parts to make them move, but it hasn't necessarily been this sort of data extraction. It's more been like, I think, one way than the other. And then while I have the floor, Amrit had a question. I thought it was a good one. Is it like the show in Silicon Valley where the main guy has a compression data algorithm? But it sounds similar to the phase change memory saving stuff.
That is a good question. So data compression is a different field, but it is complementary. So data compression and phase change memory achieve the same thing in different ways. So with phase change memory, you have the same information, the string of ones and zeros, and that's constant, and we can put it into less devices. But with data compression, we're asking, if I have this long string of ones and zeros, can I actually see patterns in it and recognize those and actually turn it into a shorter string of ones and zeros that still has the same amount of information in it? So one obvious example of data compression would be if I had a string of all ones, I should just represent that as, the number of ones that I have, right? And some indication that it's a one. So if I have a million ones, all I need is the number a million. I don't need a million different boxes to put electrons in. So that's the difference between data compression and phase change memory. But if you use both in tandem, if you compress your data and also are able to put that same data into less boxes, then we're starting to reach the limits of what's possible in computing today. How much data can we put into boxes?
Thank you.
I have a question. Hopefully I'm not cutting anyone off. But I'm curious, Dennis, what are the hurdles for this to becoming just daily use in all our computers? I'm curious about heat, how reading and writing, how much heat it creates, how much energy is needed. I'm just curious what the next steps are.
These are fantastic questions. These are the questions that researchers today are asking, and it's really what I'm trying to answer. So heat is very cool. The answer to it is cool, in my opinion. So these changes are made by heat, the phase changes, and you actually have to get up to about 600 Celsius to change the phase in memory, which sounds insane, but it can be done in computers, and it has been done in computers because it's lightning fast. You can get up there super quickly, and then you go right back down. If you're heating up a small enough area, the amounts of energy required to do so aren't that high, and they don't spread. So this has been shown in full-scale computing systems, but in terms of what's holding us back, I guess part of the answer is something called endurance. That's maybe one of the big challenges in a lot of these new emerging memory technologies today, and that's how many times can I write new data to this memory cell before it breaks. And so if you're optimistic, the answer for phase change memory is usually about 1 billion times. And for many applications, that's not going to cut it. But for applications like neural networks, what you typically are doing is you are writing a single value and then reading that value over and over. So you have to save the value, and reading isn't nearly as damaging to cells as writing is, because it's not switching between the two different states. And then the third thing, I didn't even touch on this, but in some memory systems, actually, I guess in all memory systems, you're going to have heat from the computing passing through the phase change memory, since computers get hot. And a question I might be interested in an answer in the future is, how does the computer getting hot affect the operation of the phase change memory? Is it going to change the switching speed, or more importantly, is it going to change its endurance? If it's always a little bit hotter than it should be, is it going to fill faster? And I don't know, and there's a lot of things we still have to answer. But a lot of major companies are interested in this broad class of, they're called non-volatile memories, emerging memory technologies. They're very hot right now. So there is a chance that that they will be in your computer 10, 20 years from now.
Awesome, great, thank you so much.
Does anyone have any other questions on this? I think it's really cool. Well, I have a question now. Yeah, exactly. How do you heat up? Emrit typed in the same question I was going to ask, which is, how are you getting up to 600 degrees in a flash like that?
That is a great question. So we have this intuition that it's hard to get up to 600 degrees, and that's because our brains always work at the macro scale. We're thinking of boxes of water that are maybe this big, and we can't really comprehend how tiny the things in nanoscience are. And this is something nanoscientists kind of have to learn over and over again. We always find ourselves using our intuition from the large scale world and applying it to the small scale world, and over again we find that it doesn't work. And of course, heating up to 600 Celsius is another example of one of those things. When a volume is tiny enough, indescribably tiny, it can actually be pretty easy to get it that hot and cool it down again, because the total amount of heat energy in that system is pretty small. But of course, people are still interested. It's not like it's nothing. So a big important part of how to make large-scale non-volatile memory or phase-change memory systems is, how do you thermally isolate? How do you block the heat from getting to the adjacent cell? How do you make sure the heat stays within the cell? And so there is, of course, a ton of research and simulation in exactly how to put phase-change memory cells next to each other in rows. I just realized there's also another question I didn't answer, which is, physically, how do we heat it? It's not like we're holding up a little lighter. But if you, one very basic and important component of electrical engineering is that every time you pass a current through anything at all, it heats up without exception. And that's because the electrons will always bump into other electrons in the material itself. And when they bump into stuff, they transfer those vibrations into that material, and those vibrations are heat. So we pass an electrical current through the material, and it bumps into the material a lot, and it heats up the material.
Okay, awesome. All right. Are there any other final questions? Oh, go ahead, Dustin.
Oh, yeah. I was curious just to pick your brain on just like the sci-fi side of this, because I've heard of like DNA computers, and I'm just curious if there's anything theoretical out there that you know of people talking about where there might be 20 different states, or maybe 30 or hundreds or thousands, just kind of like go sci-fi. What's the craziest thing may be possible?
So DNA memory is a thing. I think it's amazing. I don't know much about it because it's not my field, but it is a class of archival memory. And what I mean by that is you write to it once and you never write to it again. But with DNA memory, I'd have to look up, I can't give you numbers off the top of my head, but you can get truly staggering densities of information. Something like you could fit, all of the information in the world, in some, pretty small volume. Just amazing amounts of data. And so people are talking about using DNA memory, to store records for, for future generations, and maybe, to send information off to other, into space or whatever, because it doesn't break down and it's super dense. So I would advise you to do your own research on DNA memory and don't take anything from me. But I think it's if you're looking for something sci-fi to to perk up kids' ears, that could be cool.
Awesome. Yeah, and I just linked a couple of articles. One is just a Wikipedia article, but then there's a Scientific American one that says DNA data storage is closer than you think. All right. Do we have any other questions, comments, concerns?
So then it's like for binary, we use 0 and 1. So if we're using DNA, that's like 4 letters. We mean that we can store tremendous amount of information. Is that correct? With 4, if binary
Well,
2.
yes, it's not just because it's 4. That does help, but the main thing is that whether it's one, each one of those is just a protein, and it's tiny.
Yeah.
It's much smaller than these memory cells we're talking about today. So it's really reaching the limits of how small something can be. The only thing smaller I can think of would be as if it was, on the order of atoms. But proteins are very close to as small as you can get. So DNA memory is always going to be much, much smaller than we can get with traditional computing.
Alrighty. I think with that, any other questions? Otherwise, we will give another round of applause to Dennis. I like my little emojis. Okay.
Thank you guys. I really appreciate you guys having me and keep on doing what you're doing. I think it's amazing.